Welcome everyone. My name is Joe Alexandersen. I'm an assistant professor at the University of Southern Denmark. I work in the section of mechanical engineering under the brand new Department of Mechanical and Electrical Engineering. So this is a new unit that our faculty has created in order to sort of collect our mechanical and electrical engineering activities, and this is especially beneficial for one of my main interests, which is electronics cooling. So I'm expecting we'll be doing a lot of interesting research these coming years. So what I will be talking about today is using a computational design tool called Topology Optimization for design of heat sinks for electronics cooling. So my research work falls under the title of what I call simulation-based design optimization. So essentially we're taking simulations, here a complex conjugate heat transfer simulation, we add it together with mathematical programming, optimization theory, and by adding the two together we get a piece of software where we're able to design a structure for a given problem using our simulation tools. So the method that I work with is called topology optimization. It stems from the solid mechanics area where it was used or still is very widely used to optimize structures to improve their stiffness, improve their strength given some material use constraints. So usually you would define your design problem, you will define the load cases that applies, and then you will iteratively improve and update the material distribution in order to get a design proposal that has an improved stiffness and only uses the required amount of material. So the way this is done is an iterative process. So each of these frames you see in this animation is one simulation, or actually several when you have multiple load cases. So what the method does is that in each point of space in the design domain here, it dictates whether this point should be a solid or a void, that is nothing. So this is then iteratively updated using optimization theory. So I have primarily done my research work within the area of electronics cooling, or rather more thermal management, heatsink design, and so on. So we all know these classical heatsink designs where we have the pin fins, straight fins, and then these more advanced slanted fins. But common to all of these, they are very cheap to produce. They are relatively good. They are often applicable to a variety of situations. There's a lot of standard geometries that you can look up in a catalog and order one that you need, as long as you pay special attention to the orientation of especially straight fin heat sinks. There are sort of three main ways of heat transfer. Of course, we also have radiation, but I've primarily looked at forced convection, natural convection, and diffusion. And my main focus has been on natural convection, which is where I have done most of my research work, so design of passive coolers. And for that I've used topology optimization, which generates in general these very complicated organic type structures that we'll look a little bit more at in a bit. So the way we do our design prioritization is a little bit different than you would normally do in, for instance, shape optimization. So we start with Navier-Stokes flow. So here we have it in non-dimensional form. Usually we would define our computational domain as a fluid domain and a solid domain. And our Navier-Stokes equations are then only applicable in the fluid domain and not in the solid domain. However, in order to do topology optimization using the density-based approach that I use, we have to do things a little bit differently. So we add this penalty term essentially, where we have some value alpha, which will depend on the location times the velocity. And then inside a true solid, we could set alpha to infinity, and that would ensure that we get 0 velocities out. So that would make this term dominate, and then our velocities would have to be identically equal to 0. So now we are extending the Navier-Stokes equations by this generalized Navier-Stokes equations that then govern both the fluid and solid domain. Inside the solid domain, we then use this large or infinite penalty parameter, and we have this to 0 in the fluid domain in order to recover the original Navier-Stokes equations. However, numerically we cannot handle infinity, so we have to set some upper bound that has to be large enough such that this term dominates the other terms, so we get velocities that are negligible. However, as we will see in a second, they will not be identically equal to 0, but we can get them small enough to not be important for the solution. So the way we then parameterize our design instead of having these two discrete domains is that we introduce a field now that varies between 0 and 1. So each point in space now has a value that varies between 0 and 1. If this value is set to 0, we get a fluid domain. If we set it to 1, we have solid, and then we will usually have some transition region where we have a value between 0 and 1. I won't go into details here, but you can find out more in the papers that are detailed in our recent review paper on topology optimization of flow-based problems. But this is sort of the way that we parameterize our design, and then it is this field that we are updating from one iteration to the next in order to update smoothly the placement of the design and the shape and the topology of the design to improve our performance. Due to this immersed geometry approach, we do get that not truly 0 velocities inside solid, as I said. So we get this continuous velocity field even though we have an obstacle down here. So here we see it in non-dimensional units, but if we look at the log-log plot or log plot, we see that the places where we have pure Navier-Stokes flow, we have an order of magnitude of the velocity of 1 because we're doing non-dimensional things here. And inside the solid, where we have this penalty term, the velocity scale will be proportional to 1 over this alpha parameter. So by increasing alpha, we can drive down the velocities inside the solid. However, we do run into some numerical issues if we have too large alpha. Remember, ideally we would have infinite, so we want to have it as high as possible, but we will run into a series of numerical issues if it's set too high. So it just needs to be high enough to make sure that the flow flows around this immersed geometry. So some of my early work was on the design of passive coolers, so passive cooling heat sinks for electronics chip. So just a single electronics chip. Here we have it modeled as a cube heat source here at the middle. And we have a cubic domain which is closed, so it's inside an enclosure. We have cold walls at the top and the sides. And then we have an insulated bottom. Then, like I said, this heat source models an electronics chip, and then the gray domain on top is where we can place conductive material in order to cool the heat source, the electronics chips, as low as possible, so to as low a temperature as possible. So these results are obtained using a large-scale three-dimensional framework, so it's done using parallel computing because we have very large problems of several million degrees of freedom. It takes around 10 hours on a small supercomputer of 1280 cores, and that's because we need to do 500 simulations in this iterative design process in order to reach these final designs down here. So just to talk about the actual results here for a second, moving from the left to the right, we have an increasing Grashof number, which sort of tells us how important the degree of natural convection is. So how important is convection compared to diffusion? So that is sort of seen in these temperature plots. We see this slow sort of diffusive temperature field for the leftmost here. And as we move to the right, we get more of a convective plume formation over the heatsink. This in turn makes that the designs change characteristic. We get these very long, slender fingers at the conductive case or the diffusive case. Then as we increase the convection, the fingers start to contract. We get secondary branching, tertiary branching, still contracting towards the heat source because the fins are not needed to be as long. They are not needed to conduct the heat as far away as possible anymore because the convection is better to remove the heat from the heat sink. After having done these initial academic studies, we moved on to an actual industrial problem. So this was a project funded by the Innovation Foundation. So in collaboration with the industrial design company Alexio and Tryde, AT Lightning was their name back then, and then my former employer DTU Mechanical Engineering. So the problem here was that this industrial design company had this idea of incorporating the passive cooling heat sinks into the design of actual lamps and projectors. So we see here that they were very fond of these lattice types designs because they were self-supportive for 3D printed. Here we see a 3D printed aluminum specimen, and also they are very aesthetically pleasing, but we wanted to see, can topology optimization improve this the performance of these passive coolers while keeping the aesthetics to a high degree. So here we see 3 optimized designs that we came up with using our large-scale topology optimization framework. They are different designs for different orientations and degrees of symmetry. I won't go into details here, but common to them all, we see that we have these elongated cross sections and they all have a cavity in the center. So especially this cavity in the center is very interesting because I haven't really seen that for heatsink designs for these similar applications. So it should be said that these are very, very large computations. So now we are up at 240 million degrees of freedom, which takes 5 days on 1,000 cores or 2 days on 2,500 cores. So this is really, we need supercomputers in order to optimize these complex geometries and these complex physics. But the cool thing about topology optimization is that it gives you some final designs here, but it can also give you insight and some general design guidelines. So if we look at the temperature plots of some of these designs, so this is one of the lattice designs that are act as our reference. Then here we have a design optimized using topology optimization with a single symmetry plane. And over here, we have several more symmetry planes in order to make it more symmetric. So here we are treating the horizontal case where the lamp is pointing in the horizontal direction. If we look at the cross-sectional temperature distribution through the heat sinks, we see that for the lattice designs, the heat is very fast heated up during the motion through the heatsink. So that makes the heat transfer here near the top very inefficient because we don't have a large temperature difference. However, for the topology optimized designs, we see this cold air being able to transfer from the outside into the top. So we're not reusing air like we are in the lattice designs. And the same over here with a larger degree of symmetry, we see that we're able to pull in fresh air from the outside to reach the top. If we look at the pressure fields, again for a cross section, we see, of course, as we would expect for the lattice designs, we get a lot of stagnation pressure regions. So we have a very high fluid resistance because the fluid keeps moving and then hitting these many features. Whereas for the topology optimized design, we get these much more open, we get these streamlined designs that draw air in and out where it is needed. And we see the true purpose of these hollow regions in the middle are actually to provide the air and a chance to accelerate or at least move without further fluid resistance. So we keep a high velocity on the top members as well. So we then took one of these designs, we had it additively manufactured in aluminium by Renishaw. We took it down in the lab, did some velocity measurements, some infrared temperature measurements, also some local temperature measurements at the base. Compared these to our numerical simulations, and we saw a very nice agreement. We saw that our optimized designs are able to provide a 26% lower LED temperature, which directly translates to a longer lifetime. And we're actually able to do that using less material, which, especially in the context of additive manufacturing, directly translates to a lower cost. So like I said earlier, right now we kind of have to use supercomputers in order to treat these complex models and these complex physics in order to do optimization on them, because we need each simulation to be very efficient, very fast, because we're going to be doing 500, maybe 1,000 in this design process. And then, of course, this is sort of restricted to academia. We are very fortunate that we have access to these machines, but if we want this technology to be used in industry, kind of have to move to a point where we are able to use this technology on a desktop or maybe a small computational cluster that some larger companies are able to have in-house. It is, of course, also a possibility to run these things on cloud computing services, which are also becoming more prominent. But if we just look at some numbers here, so we have 24 million degrees of freedom, 2 days using 2,500 cores. We want to speed this up, and that needs simplified models, because these high fidelity models, they are just expensive, computationally expensive, but we still need these simplified models to be accurate enough to treat the problems that we want to optimize. So we developed a model that I won't go into details here, but essentially it's a potential flow model. We're able to reduce from 5 to 2 degrees of freedom per node in our computational model. So that means that what would earlier take 9 hours on 500 cores now takes only 1 hour on 500 cores using the simplified model, or 13 hours on 40 cores. So 40 cores is within the realm of industrial scales, and 13 hours is basically overnight or during an office day, or long office day, of course. But you know, you can actually would potentially be able to follow along during the workday to see how your design changes and maybe update some boundary conditions and so on. So all this previous work has been done on just a single electronics component and a single chip. So a CPU, for instance, or a LED lamp was one of the examples. But how about when we move to full electronics cabinets? So here I will look at vertical electronics cabinets, which are quite common in telecommunication, where we will use the natural convection again in order to cool the electronics chips, but we will have a very complex interaction between the plumes of the various electronics components. We get this complex flow movement, and then the question is, are standard heat sinks sufficient for cases like this, and should every heatsink be the same? So should this chip have the same as this, and should these set of chips have the same as this set? This I tried to look into, so now I just have 4 equal chips, but still we have an inlet to the right here and an outlet to the left, and then each of these chips is a heat source of 1 watt. And then the green areas are where we can place material in order to optimize our heat sinks. So this is using the approximate model that I discussed before, that is able to boil it down to only the most necessary sort of flow physics. We get that we have this mostly pin fins out of this design. They are mostly straight, and we actually see that the distribution of material is more or less evenly distributed between the four electronics components. This is an approximate model, however, and it's a potential flow model, so we get this very even distribution of the flow. The flow is very quickly distributed across the electronics, the cabinet, and we get the largest velocities between the members, which of course gives us very nice cooling. However, if we recompute the velocity field and the temperature field using the full model, so that would be Navier-Stokes equations, we see that actually inertia is very dominant for this problem. We get this largest velocity across the diagonal, and then we only get some secondary flow out here. We even get some recirculation in the corners. So that actually shows our potential model where we actually throw away inertia is not really good enough to handle this particular case on its own. So we also see that the cold air here coming in at the bottom is not well distributed because we have this main flow across the diagonal. So these two off diagonal heat sinks do not get as much cold air and thus do not cool as efficiently. So what happens if we optimize using this full model? Well, we see that we get much more complicated structures here. We get elongated fins that have these elongated cross-sectional areas that are sort of there to direct the flow, be streamlined. They're curved to accommodate the flow, and we actually see that we have more conductive material on the two components away from the main diagonal flow, because here the conductivity is more beneficial where we can rely more on convection on the main diagonal. If we compare the two, the most sort of drastic change is the computational time is extremely expensive for the Navier-Stokes solution. However, we do get a significantly lower mean temperature than compared to using the normal or the reduced simplified model. However, the question is then, can we do something in between the two here? So here we have the sort of two bounds, and then we can try to couple the two models in a hybrid optimization approach. So here we use the full model in the initial part of the optimization. So we start using a high fidelity model, then we switch to the low fidelity model. We can do that in two different ways. We see that instead of these very straight fins, we do get some of this sort of flow informed geometries from the full order model. We do get significantly better than compared to only using the simplified model, but of course the computational time also increases quite a lot. So how do we then proceed from here to larger fluxes and higher velocities? So everything I've talked about here previously is steady state. So how about when things become transient? We get unstable, transient, turbulent flow, fluctuating temperatures, fluctuating heat sources even. Then we need time-dependent solvers and optimization. And this just becomes very expensive computationally. As I said earlier, we are doing many hundreds of simulations in this design process, so we need each simulation to be efficient and fast. And for time-dependent problems, this is just very difficult because you have to step through the entire time history, and that gets very expensive very fast. So we need a combination of high performance computing and simplified models, and together with these two, I believe that we're able to push the state of the art and make time-dependent conjugate heat transfer optimization more plausible in the future. So one of the initial steps we did here was we used a pseudo 3D transient model for forced convection heat transfer. So we have we're going back to these extruded type heat fins. So it's going to be extruded in this direction here. We have a heat source, so our electronics chip, and then a flow channel. So what we're going to do is we're going to define a layer in the middle, sort of take the cross section here and extract, and then this is what we're going to be optimizing and simulating. So we make a simplified model where instead of simulating the full 3D domain, we are only modeling the mid-plane and the heat source layer, and then we're coupling these using some models. And the goal here is then to minimize the temperature after a short time. So we want instantaneous performance, whereas all the previous work has been on steady state performance. So like I said, this requires time-dependent simulation, which is expensive. And then we've used this model by Hertel et al. That we have extended to time-dependent simulations. Yeah, we have one of our optimized designs. So blue dictates solid aluminum and red is fluid channels. So here it's actually air cooling. So here we see the velocity field and the temperature field after 1 second, sorry. So actually we're looking at a very short time span. We want to lower the temperature as fast as possible or as much as possible after 1 second. So we see that our optimized designs perform better than these sort of reference geometries with similar properties otherwise, but we get a lower temperature after 1 second. If we then want to compare it to steady state cooling, we get a result like this. So we see this is much more streamlined. We have these sharp sort of aerofoil type features, and we actually don't use all of the material that we're allowed, because now the convection is sort of the dominant, where for the instantaneous cooling effect, we also have some heat capacity type deal, so a thermal storage that becomes important. So if we compare on the short time scale, our instantaneously optimized design vastly outperforms the steady state design. But if we look at the long-term performance, the steady state performance, the steady state optimized design actually performs significantly better. So we get this better in short time behavior at the cost of a significantly worse long time behavior. But in the electronics sort of situation, you will often have chips will turn on and off intermittently. They won't be exerting the same thermal load for long times. So this instantaneous temperature will actually be more interesting. But of course, this is just the beginning of this work, and there is more to be done here. So conclusions to round off is that topology optimization is a very viable method for heatsink design. But right now it sort of requires supercomputers for full fidelity. So that's why we introduce simplified models, and this render it plausible in industrial timescales. But the accuracy is of course limited to certain cases because we're essentially simplifying the physics. The computational time is still the bottleneck for time-dependent problems, but simplified models will probably be an important step in this direction. And with that, I thank you all for listening, and here is a list of references. So I'll especially focus on this, our review paper, which will sort of give an overall introduction to the field and an overview of what has been happening since the first paper in 2003 up until January 2020 this year. Thanks.